Today, I will tell you about my current LIT incoming scientist project, which brought me to the JKU. This project, shortly called SeamBioF, is about seamless polymer electrolyte interfaces for activation of living cells. And since the most critical part of actually various kinds of implantable medical devices is the interface to the biological tissue, it is essential to understand such solid-liquid interfaces under operational conditions. And for this, we have developed a unique spectroscopic inoperando tool. The big picture that motivates the SeamBioF project, this is to restore light sensitivity in degenerated retina of vision-impaired people. There are millions of people that suffer from diseases gradually leading to blindness, and there's no cure for them. But prosthetic treatment with retinal implants is possible to replace the photoreceptors, the light-sensitive part of the retina. Currently available are implants based on silicon chips that require an electrical stimulus, which is delivered by a wiring system additionally mounted inside the head. But actually, these wired implants have been discontinued in 2019 due to the lack of technological progress. Instead, a brain implant is under exploration at one of the companies. Photovoltaic implants are under consideration in clinical trials, making electrical wiring inside the head obsolete. But yet goggles are required to convert ambient light stimulus into a signal strong enough to excite the silicon chips inside the eye. Under research development are photovoltaic retinal implants based on polymeric organic semiconductors, which are also used for organic solar cells. Photovoltaic means that upon illumination of the device, an electrical signal is directly generated within the photoactive layer, which is then transmitted to the remaining healthy tissue. The interface between the device and the biological tissue is mostly important. Studying the solid-liquid interface between the device and the physiological electrolytic medium, this is what our contribution to the field of research at JKU is about. Let's start with some fun facts about human vision and vision prosthetics. Photoreceptors are the light-sensitive part of the retina, which convert photons into a processable stimulus to evoke a visual impression. There are about 125 million rods and 7 million cones. Rods are very light-sensitive, but allow only monochrome vision, while the cones allow for color vision. The question is now, how many megapixels has a human eye to quantify the resolution of human vision? Is this 125 million rods plus 7 million cones? Does this mean 132 megapixels? Well, rods and cones are not distributed evenly within the retina, and the eye is constantly moving to scan a scenery with the sharpest central field of view. If you stitch these scans together, then the resolution rather exceeds 500 megapixels. But there are only about 1 million nerve axons that can process the signal to the brain. So there actually is no reasonable answer to this question. The resolution of human vision cannot be quantified by pixel counting. Light is an electromagnetic wave, and the spectral range that is visible for the human eye covers a wavelength range from approximately 0.4 to 0.8 micrometers. A human rod is about 25 micrometers long and 1 to 2 micrometers wide, and it contains about 100 million of light-capturing molecules. The light needs to be trapped inside a rod by total internal reflection to be captured efficiently by the pigment molecules. If the rods become smaller than the diameter of the wavelengths of the visible light, let's say smaller than a micrometer in diameter, then they would become leaky to neighboring rods in close proximity. This is given by the wave nature of light, which thereby sets a fundamental limit to the resolution of vision. For retinal implants, the number of pixels is a fixed given value. The Argus 2 retinal implant contains 60 pixels. The Alpha AMS contains 1,600 pixels. And note here that we are not discussing megapixels anymore, but just pixels. So the only photovoltaic device, the Prima retinal implant, contains 378 pixels with a diameter of 100 micrometer, which are distributed evenly over an area of 2 by 2 millimeters. And now stretch out your arm and make a fist. And the area of the fist, this is the maximum field of view that is obtained by such a retinal implant. The photovoltaic polyretina device attempts to increase resolution and the field of view by placing approximately 10,500 pixels on a dome-shaped flexible support with a diameter of 13 millimeters to follow the curvature of the human eyeball. But note that this device has up to now not been tested on patients, only ex vivo experiments have been conducted. So let's check the sensitivity, that is how much light intensity is needed for a human eye and for a retinal implant to make a visual impression. The dynamic range of a human eye covers 10 orders of magnitude with respect to light intensity. This is from bright sunlight down to illumination with less than starlight. Actually, the human eye is able to detect single photons. The dynamic range of a photovoltaic pixel, at least in principle, can cover about 5 orders of magnitude, and it requires a certain light intensity to operate. It works on room light conditions up to light that is certainly brighter than sunlight. The operational light intensity for the photovoltaic prima device is about 3 times brighter than glistening sunlight. For the ex vivo testing conditions of the polyretina photovoltaic device, the illumination intensity is about 23 times brighter than glistening sunlight. However, the resolution of human vision depends on seeing contrast between 2 objects rather than seeing absolute intensity. If the contrast ratio goes down to 0, then these objects can no longer be resolved as 2 different objects. In the end, the contrast transfer function is limited by diffraction, and that is again the wave nature of light. Under dim light conditions, the contrast ratio threshold goes up. This is because of additional gain mechanism that require several photoreceptors to respond independently to come over the stimulation threshold. And now let's finally turn to our research happening at JKU, which covers only a prototypical single pixel level. So our contribution targets basic research on the development of a photovoltaic pixel that is based on organic semiconductors. The organic semiconductors are the light-sensitive part of the device. Our material of choice are small molecular compounds, so-called squarine dyes, which exhibit strong excitonic interaction with light. Photovoltaic means that the electrical signal is directly generated by the device upon illumination with light. This means light comes in, an electrical bias or say stimulus goes out, and this avoids wiring and an external power supply. The photovoltaic pixel is supposed to restore light sensitivity only. That means it should replace only the degenerated photoreceptors, while all projecting neurons are still functional. Therefore, the device should provide a safe stimulation to the remaining healthy tissue, requiring only a low-intensity light trigger. And it is the functional interface that determines both the stimulus transduction mechanism and also the efficiency of the stimulus transduction. A polymer-based electrode is supposed to form a seamless junction between the photovoltaic layer and the living cells, and only a low light intensity should be required for the stimulus transduction. So to understand the transduction properties under operational conditions of the polymer electrode better, we use a special in operando spectroscopic technique. This spectroscopic tool studies the most critical part of the device, which is the solid-liquid interface. To prove the device concept under more realistic conditions, I have initiated a collaboration with biophysics at JKU. Here, living cells are grown on the device, and their active response to the photostimulation from the device will be probed by electrophysiological patch clamp recordings. The present strategy to obtain a better stimulus transduction from the photovoltaic layer is to reduce the required intensity of illumination. For this, we utilize a polymer electrode consisting of the conductive polymer blend P.PSS, which is chemically cross-linked for stability in the wet physiological environment. This polymer electrode swells in water and soaks up ions from the electrolyte. By this, it is capable of a mixed capacitive and ionic charge injection into the electrolyte. Ionic conductance is the natural charge transport mechanism of neuronal cells, which makes this polymer electrode a very promising candidate for a seamless charge mediator. We have worked out a preliminary electrode design, which is the double layer design. It consists of 2 consecutive layers of different p-dot formulations. The reason for this sequential architecture is the difference in polarity of the organic semiconductor and the aqueous electrolytic environment. The organic semiconductor is hydrophobic, and for good adhesion, the less polar CPP formulation is coated as adhesion layer first. And then the hydrophilic pH 1000 formulation can be coated on top. The pH 1000 is highly conductive due to its capability to swell in water and to soak and release dissolved ions. But let's have a look at the bottom of the device. There's an electrode as well to support the photovoltaic effect. For convenience, we use the commercial indium tin oxide or ITO electrode, which is omnipresent in organic electronics. But how useful is such an ITO electrode in the wet electrolytic environment of a bioelectronic device? This brings me to the methodological aspect of the project, which is the in operando spectroscopy of solid-liquid biofunctional interfaces. Typically, the conductivity of a thin film electrode, such as an ITO electrode, is measured by conventional electrical van der Pauw method, which could not work in an electrolytic environment. Our in operando spectroscopy approach works under dry and wet conditions and provides multiple information simultaneously. It combines optical spectroscopic ellipsometry and electrochemical analysis. Spectroscopic ellipsometry is a virtual contactless optical method, probing the sample properties with a polarized light beam. From the measured data, several information about the sample can be extracted by fitting and modeling of the data, such as optical appearance, layer thickness, and resistivity. This still is not all. The electrochemical analysis allows to simulate the electrical bias that would come from the photovoltaic layer upon illumination. Now we can really characterize the bioelectrode under its true operational conditions. So let's see the characterization of an ITO electrode under safe operational conditions. On the left side, you see a voltage bias is applied running in a cyclic fashion while the current is probed, and that is why it's called cyclic voltammetry. In reverse bias direction, a reduction reaction can happen, while in forward bias direction, an oxidation can happen. The time running in seconds tells you about the progress of the experiment in time. Simultaneously, a polarized light beam probes the optical and electrical properties of the ITO sample under voltage bias by changing its own polarization properties. The value psi, which is plotted against the wavelength of the probe beam, this is a rather abstract value, and modeling is required to extract the sample properties. Simply speaking, the peak at short wavelength tells you something about the color of the sample, and the peak at longer wavelength, called Drude term, tells you about the resistivity of the sample. Here you can see no change for the ellipsometric recording, and this means that the sample, here the ITO electrode, remains unchanged and stable under the applied bias conditions. So now the experimental conditions have been changed, and the voltage bias range is extended to more negative bias. This time in reverse bias, for a negative bias exceeding -1 volt, there's a change noticeable within the ellipsometric data. The change is not recovered when scanning in the opposite, the forward bias direction. Instead, it becomes more pronounced when performing another cycle into the reverse bias. This is a picture of the ITO electrode sample for this experiment. The faintly colored area is the pristine, unreacted, and transparent ITO. The brownish colored area is the part of the sample that has been degraded under the electrochemical bias. And clearly you can see the material has lost its transparency. From this experiment, we can learn that there's only a limited voltage bias range which an ITO electrode can tolerate in an electrolytic environment. And this brings me already to my summary. I've shown you our spectroscopic approach to understand the functionality of bioelectronic interfaces, which are designed to act as artificial photovoltaic photoreceptors, at least at some point in the future. Currently, the required intensity of the illuminating light for such a photovoltaic pixel is way too high. The design aspect targets the stimulus transduction from the photovoltaic layer towards living cells by applying a seamless polymer electrode. In general, also for other implantable biomedical tools, the interface between the device and the biological tissue is mostly important. And therefore, the interface requires further attention than available by default characterization. For this, we currently elaborate on a special in operando spectroscopic tool, which allows a comprehensive characterization of a solid-liquid interface under operational conditions. And now let me thank you for your attention.